Good morning, everybody. And on behalf of ETN, I intend to welcome you to the second episode of our CCS webinar series. My name is Nicola Cairo, Project Officer at ETN Global, and also the Officer of ETN in charge of supporting the implementation of the activities of our CCS task force, which was launched about 2 years ago following the October workshop in Berlin. So today, at our episode, we are having two presentations. The first one from ENGIE Laborelec on flue gas characterization, and the second one on the efficiency from University of Mons. So with no further delays, I'd like to give the floor to Hélène from ENGIE Laborelec. Hélène, please feel free to share your screen, and thank you for being here today.
Can you see my screen?
Yes.
Yes, we do see your screen.
Good morning,
Thank you.
everybody. I will present with my colleague on.
Yes, I will start with a very short introduction that gives a bit the global picture of carbon capture and why nowadays the topic of flue gas characterization for the purpose of carbon capture is such a more than ever important topic. Next slide, Hélène. If we look to carbon capture, it's actually an existing process already applied since the 1960s in the US, which consists really in separating CO2 from other gases and purify it for subsequent use or storage. If we look to the picture in Europe, because regulatory framework is an important cadre for carbon capture deployment, the reason to do carbon capture can be justified by different kind of value chain or business, I would say. And the first important point is when starting from point source is the question whether we have a fossil CO2 or biogenic CO2. And depending on the utilization, CCU route or the CCS, we can create different business case, I would say. Starting from fossil, can you come back? Starting from fossil CO2, CCS is the natural route, especially for the sector that are under ETS. And the big question there is the competitiveness of CCS as regard to EU ETS tax. When we talk about utilization, if we look to the specific CCU process, such as e-fuel production, we have really to have in mind the Renewable Directive that sets somehow the limitation of the type of CO2 we can use starting from 2030. And so that can push further biogenic CO2. And we see that nowadays on this kind of project, the willingness to pay can be higher for biogenic CO2, considering also the availability, which can be limited. And knowing that starting from biogenic CO2, we can have also competitive route, which is when combined with CCS, you can really generate carbon dioxide removal that is today exchangeable on voluntary market, and that is now being also framed within the CRCF regulatory framework that is going to be released this year, and most probably it's going to align with the EU ETS in the medium term. When we look to the technology of carbon capture, you can go to the next slide. It was really driven in the 60s in the US, mostly by natural gas processing sector and so on. And really in 2006, it has boomed, and also in Europe. And back then, and if we look to that, it was really boom thanks to the energy sector, actually. Most of the application was linked to coal-fired power application. And the technology that really emerged as the most mature today was post-combustion carbon capture because of the retrofit, and a lot of projects back then were actually retrofit projects, the difference of nowadays for the energy sector. And we look to the global picture of technology for post-combustion capture. Since 2006, nothing new happened. We have the chemical absorption process, physical adsorption, membrane, cryogeny, with each the domain of competitiveness and maturity, which is strongly related to the CO2 content in the flue gas. But what we see today is that carbon capture after a valley of death, is again back strongly in the picture since 2020. But we see that it is mostly driven by the industrial application, especially in Europe. The situation can be a bit different in the UK, in the US. And we see also that industrial application has brought also the emergence of technology that were in the past more related to higher CO2 concentration, that are also now developing for lower concentration range, and so go beyond the domain of maturity and competitiveness. More and more are talking about that to hope and hoping to reduce strongly capture cost. And next slide. Which introduce the point of flue gas characterization. While 10, 15 years ago, all the research application or the test that was done at pilot was really focusing on coal-fired power application. That is today a very well-known capture applications. We look now today at the industrial application, and the challenge over there is that in integrating carbon capture in the industrial process is that industrial process can be much more complex in terms of emission points, the concentration of CO2, but not only the impurities that exist in this flue gas. And you can see typically here two sectors that are pretty challenging to this regard is the iron and steel plants and refinery plants. When we look to such an industrial plant, we have actually on site not one point source, but multiple point source with very different composition in terms of CO2 concentration or impurities. And so it's really important to well understand and be able to characterize it, because it's going to impact on the choice of carbon capture technologies and its performance.
So indeed, as mentioned by Anh, in the flue gas, there are several components which can impact the performance of the carbon capture plant, both in terms of operational performance, but also in terms of environmental and also safety aspect. And so depending on the process itself, but also depending on the flue gas treatment. So if we are considering, for example, a waste to energy plant, the conclusion will not be the same, because all the flue gas pretreatment which is implemented need to be assessed. And so basically the characteristic of the flue gas can be different in terms of flow, in terms of temperature, pressure, but also, and this is what I'm going to talk about, the composition of the flue gas in terms of impurities. So besides the main component, there are different types of impurities which can be present in the flue gas and which can have an impact on the operation of the carbon capture plant. So usually the main impurities which are commonly, I would say, monitored for more legal measurements, you find CO, dust, also NOx, SO2. But besides these impurities, other type of impurities, for base impurities, acid gas, etc., can also strongly impact and have some consequence on the operation. So in terms of impact, solvent degradation is one of the most important. So for example, if you have a high concentration of oxygen in the flue gas, that will result in an increased oxidative degradation of the solvent. The same if you have trace of metals at ppb level, so very low concentration, that can have also impact on the solvent stability, because it will have a catalytic effect on the solvent degradation. There are also other type of mechanism for the degradation, like the formation of heat stable salts in presence of NO2 or SO2, acid gas. And you can also form, for example, nitrosamines in the case of the presence of NO2 and with specific type of amine present in the solvent. And so all that has a cost, because first you will decrease the capture efficiency, but you can also have some problem in terms of emission, for example, for ammonia aldehydes, and you will generate also more waste from the degraded solvent, which at the end represent a cost for the plant operation. Then these impurities can also end up in the effluent, because when in the first step of the capture installation, the first step is you cool down the flue gas in a direct contact cooler, and so you will generate a lot of effluent of wastewater from the flue gas condensation. And so in this effluent, you can find some trace of impurities like nitrate, nitrates, sulfate, sulfate, and also metals. And all this we need to be characterized in order to be properly handled for post-treatment for the environmental perspective. So it's very important to have a deep understanding of the flue gas composition, first for the design phase, because that will trigger actually the design of the carbon capture plant, but also the need for the flue gas pretreatment to be implemented. It's also important to have emission measurement during the implementation phase, first to ensure the performance of the installation and also for troubleshooting aspects. So in our team, we have decided to focus on three main types of analysis in order to have, I would say, a relatively deep understanding of the flue gas, and that is very important at the beginning of a process. So we are using a FTIR in order to characterize the organics and inorganics in the flue gas. That gives us the real-time profile of the gas composition with the main component, but also of the impurities, trace of ammonia, etc. And more specifically, we have two methods. So the SO3 determination, what I will discuss a bit later, which is a very important parameters to be monitored when considering the problematic of aerosol. And the second one, also with this regard, is the electrical low pressure impactors, which give insight on the size and the number of the particles in the flue gas. So in order to have reliable results, it's very important that the measurements are performed according to the standards. So I will take the example of this SO3 measurement because it's quite a challenging one. And so basically in the standards from the German VDI 2462, the method to measure this SO3 is based on manual condensation. So basically, you extract the flue gas with a heated probe, and then the SO3 is selectively absorbed under the form of H2SO4 by, SO3 reacts very easily with the humidity present in the flue gas, and it's hydrolyzed into sulfuric acid. So it's selectively absorbed on this coil. And then you can complement with some impingers to measure the SO2. So you can, with this method, measure selectively the SO3 from the SO2. As I mentioned, this method is very challenging because first, SO3 is usually present at low concentration. We are talking about sub-ppm in a matrix where you have a very high concentration of SO2 with a factor of 100 times higher compared to SO2. The second challenge is that SO3 reacts very easily with the humidity, and if you have any cold points on your sampling system, then the SO3 will be hydrolyzed and condensed as H2SO4, but in another part of the system. And finally, but not the least, if SO3 is present as sulfuric acid aerosol, then the capture of this aerosol is quite challenging. So related to this aerosol problematic, so this is a phenomenon I mentioned before. So this is a phenomenon which occurred when you have very thin particles or if you have SO3 in the flue gas. These actually serve as a nuclei for the formation of this aerosol. And that can result if you implement amine-based carbon capture plant without mitigation strategies, that would result in amine emission. Because when they are present in the flue gas upstream the absorber, this aerosol grow inside this absorption column and will absorb consequently water, amine, and CO2, and successfully. And so it's very important at early stage to identify the presence of these particulate matters or sulfuric acid aerosol in order to implement the right mitigation strategy, the right flue gas pretreatment. And so for that, we are using this electrical low pressure impactor. So basically with this equipment, that allows to give the number of particles. So this is not the mass, but really the number of particles for different stage, so different size. And the one which are very important to be evaluated is the one on the stage for the particles between 0.1 and 0.3 micrometer. Because if you have large particles. This one, when they will grow, they will be captured with the conventional demisters. Contrary to these very thin particles, so even if when they grow inside the absorber, this will remain very at small scale and will not be captured by conventional demister. Just as an illustration, so this is a simplified model which has been developed by my colleague some years ago. So basically, based on the experience, based on the knowledge and different measurements, it developed a simplified model which allows to give some insight on the risk or not of amine mist formation, depending on the number of the particles. So this model was based on the solvent MEA. But voilà, besides that, you need also to have a deep understanding of the flue gas treatment which is in place, the flue gas treatment which will be implemented to assess if there is a risk or not. Emission measurements enables also to evaluate the impact of the existing flue gas pretreatment which is in place. To illustrate that, I will give the example of previous measurement we did at a coal-fired power plant some years ago. This plant had the particularities to have a different type of flue gas treatment on two parallel lines. So on one line, you have only SCR, ESP, and then the flue gas is directly quenched in this wet FGD. While in the other one, you have between the ESP and the wet FGD a gas heater, which enables to have first a cooling of the flue gas before it's introduced in this wet FGD. And that has a very big impact on the risk or not of aerosol. You can see in the first train, in that case, so with for flue gas from a coal-fired plant, so you have quite a relatively high concentration of SO3. And in that case, as you decrease the flue gas temperature in the wet FGD from the temperature above the acid dew point down to 52, in that case, you have supersaturation conditions. So you will create this thin acid sulfuric aerosol, as it is shown on that graph with this red curve. So with voilà, number of aerosol on the 1 to the 7th particles. In the other end, when you have this gas heater, first you cool down the flue gas below the acid dew point before to go into the wet FGD. And as you can see, that has an impact because on that location, after that, you can see that you don't form this sulfuric acid or aerosol because this has been initially condensed on this gas heater. So you don't have the problematic of aerosol in that case. You can have in the other end some problematic of corrosion for the gas heater. So you will need to implement some material resistant to that. There are also several mitigation strategies which exist also to eliminate these thin particles in the flue gas. The first one, which is considered by most of the suppliers, is the wet ESP. So if it's operated in the optimal condition and provided you don't have a too high concentration of SO2 in the flue gas, that enables to significantly reduce the risk of aerosol formation in the flue gas and thus to have lower impact on the amine emission. The second mitigation strategies is the use of a Brownian demister unit. This is actually this type of strategy which has been implemented at TCM, which is one of the largest pilot infrastructure in Europe. And as you can observe, that reduces the level of aerosol by a factor of 100. Emission measurements are also critical when you need to validate new technologies. So I will take the example of the LEILAC-2 collaborative project. Basically, as you probably know, for cement application, there are two types of CO2 emission. The one which are related to the combustion of the fuel and the one from the process itself during the calcination of the limestone. And so the objective of this LEILAC-2 project is to demonstrate the process which has been developed by Calix, which is based on an indirect calcination, heated calcination. So that means that the CO2 emission from the process are separated from the one for the fuel consumption. And in such infrastructure, you will produce a very concentrated CO2 stream. So in that case, you need to adjust the sampling system for analyzing such a matrix. You have a high CO2 concentration, you have also different type of impurities. So you really need for the emission part to define, depending on the matrix, the right equipment. And regarding the topic of emission, I will finish on the CO2 quality, because this is actually the challenge for tomorrow, as it will be important to have some reliable, accurate, and sensitive analytical tools to be able to monitor very thin, the level of impurities at very low level. Because in one hand, depending on the source of CO2, depending on the capture technology and the post-treatment, so if you have an amine-based carbon capture, or if you are implementing an adsorption technology, then the level and the nature of the impurities which will be released in the CO2 will be different. And on the other hand, the CO2 quality, which are required for transport and storage application, but also for e-fuel, are becoming more and more stringent. For example, you will need to have very strict level in terms of oxygen, humidity for transport and storage. For e-fuel, the requirements in terms of sulfur inside your CO2 quality are very strict. We are talking about ppb level. So it's very important to identify what will be the most relevant online and offline methodologies for the analysis of the CO2 quality. Not only to be sure that your carbon capture plant is operating in the way it should operate, but also for contractual guarantees. You need to prove that the CO2 quality is in accordance with the one which are required. And to finish, I would say we believe also that testing CO2 capture in representative condition at pilot scale is very an important step for de-risking the carbon capture before large-scale application. Because first, it enables to test in real condition with real flue gas the carbon capture. It provides also experimental data, which are, I would say, very useful during the discussion for the permitting aspect. So you can have data on emission, on condensate. Also, depending on the accessibility of the proprietary solvent, that's a very sensitive I would say, information from the supplier. So if it's possible to test some proprietary solvents, so this is very important to validate the performance of such solvent independently from the supplier. And we can also test some advanced configuration before large-scale application, for example, packing, different type of packing. And finally, for the case of, for example, CCGT application, such a set is very useful tool to evaluate the challenge and the opportunities when considering the dynamic operation of the carbon capture. Well, so that's at the end of the presentation.
Thank you, Hélène. Thank you, Han. Before moving to the question and answers, I would give the floor also to Antoine for his presentation, and then we open the question and answers with the presenters. So thank you again to our representatives from ENGIE Laborelec for their participation. Very appreciated. Antoine, please, the floor is yours.
Yes, thank you. Do you see my screen?
Yes.
Do you see my screen?
Yes.
Okay, nice. Okay, so how to retrofit an existing combined cycle gas turbine with post-combustion carbon capture? What is the impact of post-combustion carbon capture on the combined cycle gas turbine? And how to reduce this energy penalty associated to the carbon capture? All these questions were addressed during my PhD thesis that I worked on during the last 4 years at University of Mons in Belgium, in the framework of the BEST project, which was a federal project in Belgium working on the energy transition. Why do we need to retrofit existing power plants? Firstly, because there are still a lot of CCGT plants which are already operated today. You can see here the new CCGT capacity which were added every year in the CCGT fleet in the world. And you can clearly see that some recent CCGTs were added in the recent years in the world. So it means that a lot of CCGT which are running are still new, are still recent. And moreover, there are still new CCGT plants which will be built in the future, or which are planned to be built in the future. So clearly, CCGT will still play a major role in the energy production in the future, and we have to address this problem of emission of the CCGT to tackle and to finally achieve the targets in terms of reduction of greenhouse gases emission. How to reduce the CO2 emission from this combined cycle gas turbine power plant? For that, there are two main approaches. We can firstly apply post-combustion carbon capture. So we capture the CO2 from the flue gases of the gas turbine by a chemical process. Or we can also think to burn directly e-fuels in the gas turbine. So we can, for example, burn hydrogen, ammonia, or blend of hydrogen and ammonia. However, this solution requires to completely change the core of the gas turbine, so the burner of the gas turbine to be able to handle 100% of hydrogen, for example, in contrast to the solution of carbon capture, which allows to keep the original component of the gas turbine. Moreover, there are still a lot of challenge with the production and the storage of e-fuels. So this solution seems to not be ready now, in contrast to post-combustion carbon capture, which appears to be the most mature solution today and the best solution to retrofit to the existing combined cycle gas turbine. So the most mature process today for post-combustion carbon capture is the amine-based post-combustion carbon capture process. This process is composed of an absorber and a stripper. In the absorber, you have the flue gases which are cooled down and then which enters at the bottom of the absorber. In the absorber, you have a solvent which reacts with the flue gases to capture the CO2 from the flue gases. Then the flue gases are released at the top with a lower CO2 content, and the solvent, the CO2 is captured. Then you have to release the CO2 from the solvent. So it's for that you have the second step, which is the regeneration step in the stripper. You have to provide heat to the stripper to break the chemical bond between the CO2 and the solvent, and to separate the CO2 from the solvent. This heat here is the main contribution to the energy consumption of the carbon capture plant, and so it will impact the overall efficiency of the carbon capture plant and of the overall efficiency of the global plant. However, applying carbon capture to gas turbine is quite challenging because gas turbines are not ideal for carbon capture application. There is a low CO2 content in flue gases between 4 and 5%, and the lower the CO2 content in flue gases, the more difficult is to capture the CO2 and the higher the energy consumption of the carbon capture plant. Moreover, the flue gas rate is quite large of flue gases coming from the CCGT. So it means that it will require very large equipment for the carbon capture process, and it will lead to very elevated costs for the carbon capture plant. Moreover, in terms of operation, as the gas turbine will be increasingly used as peaking units to back up renewable production, they will mainly operate at park load, and they will increase also their transition phases, such as startup, shutdown, load variation. And all these design conditions can impact negatively the performance of the plant. So the main two research questions were first, to what extent applying carbon capture penalizes plant performance and flexibility, and secondly, how to reduce the carbon capture energy penalty linked to the carbon capture system. We will first look at the first point. So for that, we considered a conventional 580 megawatts combined cycle gas turbine plant. So you have the gas turbine and then the steam cycle, which is at 3 pressure level, and which we read steam cycle. The electrical efficiency of this CCGT is 60.7%, and we modeled this CCGT plant using the ThermoFlow software. So we have this combined cycle gas turbine. In the flue gases, we have 4.6 CO2 percent of CO2 in volume basis, and we want to capture this CO2. So for that, we will apply the amine-based carbon capture process. We need to provide heat to the process, electricity, and we want to capture 90% of the CO2. So the objective is to determine what is the overall efficiency of this system. So for that, we had to model the carbon capture unit. So for that, we use the Aspen Plus software, which allows to do thermodynamic cycle simulation. And we had also to design the plant. So just to give you an order of magnitude, here as the dimension of the carbon capture system for treating the flue gases coming from the studied combined cycle gas turbine power plant. You can see that here for the diameter of the absorber, we have 18 meters and 30 meters for the height of the absorber. And for the stripper, we have 8.5 meters for the diameter and 30 meters for the height of the stripper. So the dimensions are huge, and this will also impact negatively the cost of the plant. Regarding the performance during the nominal operation, we finally obtained by considering the carbon capture process and using the conventional and the benchmark solvent, which is monoethanolamine, so MEA. We can see that we reduce the electrical efficiency to 47.2%. So compared to the case without carbon capture, we have a reduction of 13.5% in efficiency. So we can very highlight the negative impact of applying carbon capture to a combined cycle gas turbine. This case was for the nominal operation, but we also looked at the part load operation, so that we compare different load operation. We compare 1%, 100% load, 75% load, and 50% load. We compared for that the energy input into the system, into the CCGT, to produce 1 kilowatt-hour of electricity. We have here the energy input for the CCGT without carbon capture, and here the CCGT with carbon capture. We can clearly observe that we have a bigger energy input for the case with carbon capture because we consume more when we apply carbon capture. And if we do the difference between the two bars, we obtain the carbon capture energy penalty for each load. And what we obtain is that finally, we can see that the carbon capture energy penalty increase when the plant loads decrease. So, for example, for 30% load, we can the energy penalty increase by 20%. So finally, we can conclude that the part load operation of the CCGT has a negative impact on the performance and on the energy consumption of the carbon capture plant, and so that the part load operation reinforced the negative impact of the carbon capture plant on the overall performance of the plant. Now we will look at different solutions to try to reduce the carbon capture energy penalty induced by the carbon capture system. So for that, we can look at different parts. We can first look at the CCGT and what we can do on the CCGT to try to facilitate the capture of CO2. For that, we have to work on the flue gases, and we will try to increase the CO2 content in flue gases before the carbon capture system to reduce the energy consumption of the carbon capture system. A solution for that is to perform exhaust gas recirculation. So we can recirculate a part of exhaust gases the inlet of the gas turbine. So we have added an EGR loop to our CCGT model. We have here the EGR loop. The EGR loop is composed of a direct contact cooler to cool down the flue gases, then a splitter in which a part of flue gases will directly go to the carbon capture system, and the other part is recirculated at the inlet of the gas turbine. There is also a blower to compensate the pressure losses in all the circuit here. And there is the EGR ratio, which is set to 35%. So we saw that the higher the EGR ratio, the higher the CO2 concentration in flue gases. However, we are limited in EGR ratio because if we increase the CO2 content in the flue gases, and so at the inlet of the combustion chamber and of the gas turbine, we will also decrease the O2 content, so the oxygen content at the inlet of the combustion chamber. And decreasing the O2 content can lead to unstable combustion, incomplete combustion, and so problems and some issues with the combustion. So if you want to go below a certain value of oxygen, we need to completely change and redesign the burner. And it's not the objective here. So we want to apply EGR without changing the core component. So it's why we are limited here to 35% EGR in this case. A side effect of EGR is that we reduce the flue gas flow rate because we recirculate a part of the flow rate into the gas turbine. It's only a share of this total flue gas flow rate, which is sent to the carbon capture system. So we can reduce, for example, the absorber from 18 meter to 15 meter, and the stripper from 8.5 to 8 meter. By doing 35% EGR, we can finally increase up to 7.1% the CO2 content in flue gases. So we increase from 4.6 to 7.1%. Then we can try to work more on the carbon capture system and try to reduce the energy consumption of the carbon capture system. For that, we can work on the solvent or work on the configuration. In this work, we more focus on the solvent, and we compare the use of two different solvents: the conventional and benchmark solvent, which is MEA, and a more advanced solvent, which is a blend of MDA and piperazine. This advanced solvent, it's a well-known solvent in the carbon capture community. It has already been studied for different applications, such as coal-fired power plant, cement plant, and these studies reported very good benefits of using MDA-PZ over MEA. And in this study, we wanted to see if the advantages of using this solvent instead of MEA were equivalent for an application with a lower CO2 content in flue gases. So finally, we obtained here this result for the carbon capture system and for the reboiler duty, which is the amount of heat that we need to provide to the regeneration column to regenerate the solvent. And we can clearly observe, according to the superpressure, that this reboiler duty is much lower for MDA-PZ than for MEA. So MDA-PZ requires much less energy to be regenerated than MEA. So it will have an impact positive on the global performance of the plant. Then we have to work also on the interface between the CCGT and the carbon capture process and the energy integration between both plants. So we know that we need heat for the carbon capture system, need for the reboiler. This heat has to be transferred into the form of steam. So we need steam for the carbon capture process. But we have steam in our steam cycle, in our CCGT plant. So the question is where to extract the steam to provide the steam to the carbon capture process. So we compare different extraction points and different approach. And finally, we obtain that the best location to extract the steam for both solvents was the IP-LP crossover in our steam cycle. So we have to extract the steam, we have to expand the steam, to deseparate the steam because we need saturated steam in the reboiler. And to deseparate the steam, we just recirculate the liquid condensate at the outlet of the reboiler. And then we can re-inject the condensate into the steam cycle. So by doing all these modifications, so by applying EGR, by extracting steam from the steam cycle, we can increase the efficiency up to 53.9% using MEA. So compared to the case with our adaptation, we reduce from 13.5 to 6.8% the efficiency penalty induced by the carbon capture process. By using MDAPZ instead of MEA, we can still increase further the efficiency. So we gain 0.5% compared to MEA. So we can see that we have an interesting gain by replacing the solvent. And for this large-scale power plant, 0.5 is non-negligible. So the main conclusion of the work were that finally implementing carbon capture to CCGTs without any adaptation strongly degrades the plant performance, and even more during part load operation. So some adaptation are needed, and we saw that the negative impact of carbon capture can be strongly reduced with some adaptation, and also without modifying the existing component of the carbon capture plant. So for example, by performing EGR and extracting steam from the IP-LP crossover, we could reduce the energy penalty from 13.5 to 6.8% using MEA. And also we can go further by replacing MEA by another solvent, a more advanced solvent, for example, like MDAPZ. And by using MDAPZ, we can increase up to 0.5. We can increase by 0.5% the efficiency. However,
Antoine, I'm sorry to interrupt you. Could you reshare your screen, please? We don't see your screen anymore. I don't know why. Maybe I think I made a mistake. Sorry.
Okay, so
thank you, David, for noticing. Yes, okay, now I can see. Yes, thank you.
I can maybe restart the conclusion, or so I will restart the conclusion to be sure. So the conclusion of the work was that implementing the carbon capture to the CCGT without any adaptation strongly degrades the plant performance, and even more during part load operation. That also the negative impact finally can be strongly reduced through some adaptations. So we need some adaptation to facilitate the application of carbon capture, and we do not modify existing component of the plant. So it's quite interesting. We can, for example, use EGR and also extract steam from the steam cycle from the IP-LP crossover. And by doing so, we could reduce the energy penalty from 13.5% to 6.8% using MEA. And then we also seen that replacing MEA with another solvent, a more advanced solvent, which is, for example, MDAPZ, results in a CCGT efficiency increase of 0.5%. But it is also quite interesting to use another solvent like MDAPZ, for example.
For their loyalty and fandom. Virgin Battle.
However, we have still some problems with part load operation, and also there is still a lot to do with transient operation as well. I think it's the most critical point for the application of carbon capture finally to CCGT is to handle this part load operation and transient operation to reduce the carbon capture penalty during this operation, and also to see if the carbon capture process is able to handle this transient operation. And finally, here we presented just technical modification, but finally, a techno-economic analysis will be needed to really assess the techno-economical viability of this adaptation and to see if it will be possible to make the application of carbon capture to combined cycle gas turbine more viable in the future. Thank you for your attention. It's the end of my presentation.
Thank you, Antoine. So we at ETN intend to thank our presenters for today, Antoine, Hélène, and Han for their excellent and insightful presentations. Thank you for your work and your availability to present this morning. We appreciated this opportunity. So as we discussed before, so we intend to open a question and answers session with our participants for about 15 minutes. Just before doing that, I am going to launch now a webinar feedback interaction. So I am going to just open a poll for requesting you, if you'd like, to provide any feedback or suggestions for future webinars to improve the quality if where appropriate. So we're looking forward to address your feedback, your comments, and provide webinars accordingly in the future. Having said that, I open the floor for any questions you may have. Please feel free to speak. Daniel, please go ahead.
Yeah, I did put it into the chat. Antoine, a question. Do you have numbers for impact on efficiency and power output of EGR alone in one of your cases?
On EGR, okay, without carbon capture, so EGR alone, so no, the blower.
No, EGR compared, no, if carbon capture without EGR and carbon capture with EGR, but not changing something else at the same time.
Okay, I have the data only for that, but the main benefit of the result that I showed you, it's due to EGR. But the comparison,
not the integration, because when I run the numbers,
integration, but I think the most important is from EGR. I do not have really the comparison with and without EGR with integration.
Okay, I'm surprised.
The first case, what without integration to be.
Because when I run the numbers on EGR, we sometimes find that we have a slight benefit on efficiency and sometimes we don't. That's now really depending on the exact configuration, gas turbine, etc., and ambient conditions. EGR has an impact on the size and efficiency of the capture plant, of course. Now there we all agree. But whether it's been balanced by the impact you have on the power plant, that was really my point. And the big part of improvement was when I really start integrating the steam from the power plant to the capture plant. That, of course, has quite some impact if I compare it to a case where I additionally produce steam from some other sources.
Yeah, EGR will really depends on the blower consumption and on at which temperature you cool down your flue gases before being rejected, and it depends on all these factors. Yeah. So if you can cool down very low your flue gases, you can reach better performance, and so the impact will be much lower on the power plant. So
it's a balance of cost, effort, and benefit. Okay, thank you.
Thank you.
Thank you, Daniel. I see Andrea. Please, Andrea.
Yep.
Go ahead.
Thanks, Antoine, for your interesting presentation. My question is related to the pressure in the capture unit. So actually, there are two questions. Which pressure have you assumed or considered for your simulations, and whether you have done a kind of sensitivity analysis to see if this pressure has an impact on the overall efficiency of the plant?
Yeah. Globally, it's always better to work at the highest possible pressure in the carbon capture unit, because I can show you on this graph. As you can see here, the higher the stripper pressure, the lower the rebubbler duty for the different solvents. However, the super pressure will also impact the steam quality, which is required for feeding the reboiler. And so if the super pressure is higher, it will require higher steam quality. And so you can impact more your steam cycle because you will extract steam of higher quality from your steam cycle, and so maybe produce less power in your steam turbine. So it's why finally with MEA we could consider the maximal super pressure, which is 2.2 bar, because by extracting from the IP crossover, this pressure was sufficient to go to 2.2 bar in the stripper of the carbon capture. But for MDA-PZ, I do not have the exact stripper pressure in mind, but it was about 2.6 or 2.5 bar for the stripper pressure, because if we want to go higher, we have to extract from another place in the steam cycle. So we have to extract, for example, intermediate pressure steam, and so it will impact more the steam cycle. So it was not a solution to go too high in stripper pressure with MDA-PZ.
Okay, thanks.
Thank you. Habi Haidar, please.
Hi, thank you. Thank you for the interesting presentations, post presentations. I have a question for Antoine. Did you take in consideration the requirements of the CO2 purity after the absorption unit?
I set the purity to 98%.
So this is
before the compression station, just at the outlet of the condenser.
Okay. So mainly you didn't adjust the compression and purification unit to purify it. So they will.
You have to consider, but it's also considered in my calculation. I didn't show it here, but it's considered in the overall efficiency.
Do you have a number amount? If let's say if you want to get that CO2 to the pipeline, then you have around 110 bars pressurizing, and you have maybe very high purity, let's say, because lately I read a number about 10 ppm for oxygen, so it's quite energy intensive.
I have to check the result. I can send you after. I don't remember by heart, but for my case, I only consider. I do not consider the compression to 110 bar. I only consider to 30 bar because in Belgium it's the recommendation of the gas network operator. So we have to inject it to only 30 bar. And there are some specification, but I can send you the details after.
Yeah, that would be great. Thank you. And one more question is, when you consider the part load operation of the cycle, how was the steam cycle, so the combined cycle? Was it exactly the same part, as the same variation as the gas turbine, or they were like not coupled exactly?
You mean the how react the steam cycle, or?
Yes, the steam generation and the steam gas turbines compared to the gas turbine. So the steam turbine and gas turbine.
The power will be reduced because you have like a sliding pressure operation. So you will reduce the pressure level automatically according to the flow rate into your steam cycle. We reduce the steam flow rate, and so reduce the steam for the production of steam turbine.
Okay.
So it's all is connected.
Thank you.
Thank you, Gadi, for your question. I propose we go with Peter and then David, and then we have maybe the space for the very last question in addition to Peter and David. Peter, please feel free.
Okay, I hope you can hear me. I have a question to Hélène and Huynh concerning the split of the contaminants which there might be in the exhaust. Is there a rule of thumb, or can you give us some numbers on whether they depending on their nature, of course, typically end up in the CO2, causing them issues with CO2 purity, or rather in the washing fluid or washing media, which would be then maybe less of an issue.
I would say it depends also on the capture technology, but for an exact, I would say split, I would not have any figure in mind. But let's say if we're considering amine-based carbon capture, so in that case, what type of impurities you can find in the CO2 would be humidity, of course, but for that you have some mitigation strategies you can implement with adsorption bed or even triethylene glycol to reduce at very low level the humidity content in the CO2. You can have also some trace of oxygen and nitrogen. We are talking more about ppm level. So let's say, it's few tenths, I would say, of ppm of oxygen and a bit more of nitrogen. Other type of impurities which can end up in the CO2 will be more related to the degradation of the components. We can find some trace of aldehydes, but that will depend also on the stability of your solvent. If your solvent degrades, then the risk to have a higher concentration of aldehyde in the CO2 can be expected, I would say. Voilà, so this is really dependent on the CO2 capture technology, because if you are targeting for other type of application for a more concentrated flue gas with CO2, if you are targeting adsorption, then the impurities which can be problematic are different.
Maybe an additional question on the cost or on the effort, on the complexity which is added or which needs to be added when you run into issues like mist formation and this kind of things. How much of the total cost of a capture unit is typically needs to be dedicated to these additional components? Do you know that?
No, I would not have any figures in terms of capex for this flue gas treatment. More compared to the overall capture plant, it will be more limited, but voilà, still it's few.
Yeah, I don't have the figure in mind, but it was the share over the cost of equipment. It is not the biggest part, knowing that you can have different mitigation options between multiple water wash, acid water wash, or Brownian demister, gas exchanger, but in all cases, it's a no-brainer for this capture. If we talk about really Eman capture, it's really a no-brainer. And when they do the design, they ask very specifically to do this distribution measurement, and it is integrated for them to decide the integration of that or not. But it's really a no-brainer to plan it when there is a suspicion of risk of aerosol emission, because it's very challenging to monitor and to control afterwards.
Maybe
Thank you.
last, sorry. You also showed physical solvent on one of your first diagrams. Is that actually water, or what do I have to think about it, the be behind it?
Physical solvent will be more for other type of application. For example, if you have a syngas, so with a mixture, these are used for syngas purification. For example, for acid gas removal.
Physical solvents are there?
Yeah. So voilà.
Yeah, if it takes too long, we can take that separate.
I can share your contact details when you want, Han and Helen, with Peter, so that Peter can reach you for further questions. I feel sorry that I have to interrupt this interesting discussion. But I also see indeed other questions from our participants. I see the last question from David.
Thank you very much. Thanks, Hélène, for that nice presentation, which described a lot of pioneering research work in this area, I think. My question is, do we need to worry about SO3 in particulate for gas turbines? Because we know that we emit less particulate than we draw into the turbine because of filtration. There's a very small amount of sulfur. So yes, a little bit of acid aerosol, but again, that's mitigated by having no particulate to nucleate onto the droplets. So I don't see that being a big issue for gas turbines. Would you agree?
Yes, I would agree. We did some measurement, just to checking in one, some years ago on the gas-fired installation, and indeed the level of aerosol was very low. Then, today the sulfur content in the natural gas is very low. Let's see in the future if it evolves with increasing share of biomethane, for example. But today I would say that the risk is for gas-fired installation low.
Yeah. Thank you. And a cheeky second question. Have you looked at the post-capture flue gas, looking at measuring the very low CO2 concentration and the stack flow under those harsh conditions?
In the treated flue gas?
Yeah.
Yeah. Not yet. We are going to do it because we, as I mentioned, we have a pilot installation, and so we have implemented some analysis to detect the CO2 on the treated flue gas, so very low. So, but voilà, it will be in operation soon next year. So we'll see that for this low. But indeed, it's very important because we need very high accuracy, and to prove that we achieve 95% capture rate. But
yeah, I wonder if you even need to think about the CO2 in the air that comes into the process, which will be a bias. But anyway, something to think about later.
Mm-hmm. Yeah.
Thank you.
Thanks to you, David and Helen. Peter, by the way, I just share with you the contact details of Helen and Han by private email. So when you also want to continue any questions you may have. If there are no further questions, we intend to thank, first of all, our presenter once again, Antoine, Han, and Hélène, for making themselves available for today's meeting, and also for sharing their knowledge and the state-of-the-art technology and research in the field of CCS. And we hope all our participants enjoy this webinar and they learn something new. And we are looking forward to welcoming you to the next webinar episode, which will take place in February 2025 with one user from the ETN community. With this, I thank you once again, and I wish you a pleasant weekend ahead. Thank you very much.